And today, still talking about holomorphic curves and maybe something about stable maps, and also why do we need such things. So last time I talked about regularity theory of holomorphic curves, and then the certain derivative estimate under small energy condition, and then the Sachs-Uhlenbeck type covering argument, which gives you certain convergence of sequence holomorphic curves under energy bound away from finite many points. And then finally, I discussed removal of singularity theorem under the assumption that energy is finite. So still, I also need to talk about this bubbling of phenomenon. So let's suppose that you have a sequence of maps from sigma Riemann surface to a almost complex manifold, so that J is compatible with certain symplectic structure. So it may be beta to f of n. So you have a sequence of them. And then let's suppose that your holomorphic curves, sorry, they are holomorphic curves, are uniformly bounded. And then last time, what I said is there exists a finite many points, P1 to PL or something inside of sigma, such that this Fn on this complement converges to something locally uniformly in CK topology for any K. Okay. So this somehow I discussed last time. And then I also say that removal of singularity theorems by removal of singularity theorem, we can also see that this F infinity actually extends to a map from CP1, to sigma 2x and J holomorphic curve. Because these maps have fine bounded energy by C, and then by Fatou theorem, this one also has bounded energy. So therefore, you get this. So here, actually, this E of F infinity, originally defined on the complement P1 to PL, is actually bounded by this constant C. So therefore, we can use this removal singularity theorem near these punctures, and then you can get it. But also, so near this P1 to PL, we can also see other curves. So around this P1 to PL, somehow we describe this sequence Fn, and then somehow we obtain other holomorphic curve, right? And then we obtain other curve, maybe, I don't know, maybe G of J from maybe C to X, and J, yeah, something. So J, in this case, maybe at the beginning, maybe 1 to L, but actually there may be more. So I will explain it a bit more carefully. But roughly, the idea is the following. So roughly speaking, so these P1, PL are the points where the derivative diverges, right? So roughly speaking, if you take this df of n at this P, Pi, and take its norm, then it actually diverges. Right? It is not really this, because they are just a kind of limit of certain sequence points, and take, yeah, maybe there is a point like a PIN, right? PIN inside of the sigma, and then your derivative, the derivative of these things. Maybe this one diverges to infinity. So this point is need not be this point pi, but roughly somehow you may just think in this way. So and then so here you have some surface heat sigma, and then you have this point pi. And then you take a coordinate neighborhood of this. You can take some coordinate neighborhood like this. And so therefore here you have complex plane, and then you have a certain disk like this. And then this one is mapped to this. So this is a coordinate chart. And from here to x, you have this Fn, right? So roughly what we do is the following. So let's take this one is equal to, say, Rn, right? And then, so here actually 0 is mapped to this pi. So maybe I denote it by coordinate psi, coordinates at psi. And then if I have point here, z, originally this z is mapped to some point here. Okay. But now I rescale the domain. I don't know, maybe I rescale the domain like this. So that now I have a point, z is actually something like this Rn of z. So this is actually a map like multiplication by 1 over n. And then if you compose this map, if you compose this map, then here the derivative is something like Rn. The magnitude of derivative is something Rn. But because here I just consider map by multiplication 1 over Rn, so therefore from here to here, somehow this map is a kind of bounded derivative. So you just rescale the domain, and then look at the new sequence. So this is actually, maybe I may just write it like a g. No, g I already erased it. It was there. So therefore maybe I just write it h of n or something. And then, so here actually, there is a little bit delicate point, because I know the size of the derivative at this point, but I don't know the size of the derivative at other points. So therefore, we need to use some argument. But anyway, so roughly speaking, this d of hn, yeah, roughly d of hn is actually bounded. And so somehow you can take the limit of this sequence, right? So, and also this Rn tends to infinity. That means this kind of domain surrounded by this yellow one is actually getting larger and larger as n tends to infinity. So therefore, originally this Hn may be defined on a finite region of in the complex plane, but Hn somehow converges to something like H infinity from complex plane to X. So for this, actually, we really need to bound the derivative, somehow control the derivative everywhere. But so roughly speaking, we have this sort of stuff. And then after that, actually, we also look at the energy of this. But energy of this Hn is same as energy of this Fn composed of psi, because if you change the domain by conformal mapping, then the area form is multiplied by some scalar square, and then the derivative of this mapping is multiplied by 1 over the scalar, but we take energy, that means integral, energy is always integral of this thing, right? So therefore, in fact, I have to write here some d of volume of something, right? Or area form, right? So the scaling effect here and scaling effect here actually cancel out. So therefore, this is actually kind of conformal invariant. So therefore, this composition has the same energy. And then use the Fatou lemma again, and then actually you can show that this one is also finite. And then by removal of singularity, you get something like CP1 to X. That's what I wrote this G something, GJ or something. So at least GI, sorry, GI. So this is a kind of rough idea, and I have to say that. So how can make this argument work? So then people often use a lemma due to Hofer. Maybe it may be a little bit too much. So to make it work, I use a lemma due to, maybe people attribute it to Hofer, or maybe sometimes maybe attribute to Eckler and Hofer, and I just give the, I don't know where I have it. Okay, so this is a little bit technical lemma, and where can I find it? So, okay, I don't know. Maybe, yeah, maybe I will come back to this later. Yes, maybe I just come back to this later. So anyway, so this one, maybe I can give you some reference later. So the rescaling actually will take place not exactly at this point, but somehow nearby point. And that nearby point, somehow you take certain, you have some neighborhood, like, yeah, if this size is epsilon node, and then there's another epsilon near this, the point, so that the energy in this neighborhood is bounded by the derivative of the central point multiplied by maybe 2 or something. And also this radius of this smaller neighborhood is somehow still not so small, so that if you multiply with this magnitude, it tends to infinity or something. So there is some lemma due to Hofer. And so this is just a rough idea, and maybe it may not be enough to tell the details, but so you can just do this. Okay, so this is one thing. So this is bubbling phenomenon. And the second thing is the somehow continuation of the discussion last time about this removal of singularities. So that is a behavior of the holomorphic curve from a long cylinder with small diameter, small image. So the next thing I have to talk about is these things. What does it mean? So last time for removal singularity, what I said is somehow you have say half cylinder like this, like a minus infinity to 0 cross S1, and then map to X. And here is a map F, the holomorphic map. And let's suppose that the energy is finite, right? then f extends to a holomorphic map, yeah, from the disk, right? From disk, yes, to disk. Namely, so this domain, this infinite cylinder, we can identify it a punctured disk. And then what I'm asking is whether this holomorphic map extends over the puncture. And the statement says that if this one has finite energy, then it extends to this. So last time I said that if you consider the kind of behavior of the energies, and then you have certain differential inequality in the end, and then from this differential inequality, you can show that actually the energy density actually decays exponentially, and so in particular it extends continuously over the puncture, and also we have a Hilda continuity, or maybe if you look at the derivative, then the derivative belongs to W1P class, and so after that, actually regularity theory tells us that this is actually a holomorphic map from the domain, from the disk. So this is the last time. So now today, what I'm talking about here is the following. So now I have a cylinder like this. So like a minus L times S1. And then map to this X and J holomorphic map. But here maybe I just write it F. And so that the image is contained in a tiny neighborhood of this, so like a B of epsilon of some point, maybe x naught. So epsilon may be certain small number here. Okay, so let's suppose that this image of F is contained in this B epsilon of x naught. Then we have a following estimate. So I have this df of tau t, and then take its norm. Then and then here tau is from say minus L plus 1 and between minus L plus 1 and L minus 1. So namely here actually the original domain is actually minus L to L, the interval minus L, but I consider a little bit smaller one. So minus L plus 1 to L minus 1. And then take its derivative, and then this one is actually bounded by some constant times e to the minus another constant c here of the minimum of L minus tau and tau plus L. Okay. So here I have minus L plus 1, and here it is L minus 1, and then I take some point here. I take some point here from here. So this is actually tau t. Then the measure the distance to these boundaries. So this distance is actually tau plus L, and this distance is L minus tau. And so it's a distance to the boundary of the domain, and then take its minimum, and then take its exponent to minus 1. So we have this sort of estimate. So last time actually we had an estimate for this. So if this one is sufficiently far away, then this one is already close to some point. And then I used certain isoperimetric inequality to bound this circle, the bound of the loop by a certain disk with area bounded by constant times the square of the length of the loop. And so you can do it for any tau, if tau is so small. And from here, you can get some differential inequality for the energy functional for the restriction of this Holmos map F. And then from this, actually you get some decay estimate for this. Once you have this, now you can use this energy derivative bound under small energy condition. And so actually, this will actually decay nice. So this is actually the argument. And here we actually use both boundaries. So that time actually I only use one because the other one is infinity, right? So we don't have any limit. We don't use this limiting B. But here we have both boundaries. So therefore somehow we have to use both. So therefore here we have this. So this is actually another thing which is also similar. Yeah, somehow you can guess from the argument for removable singularity theorem. So these two are the supplements which I want to mention at the beginning today. Okay. So now I start discussing. Now I start discussing the stable maps. Okay. Okay, so today, stable maps. So stable maps, the notion introduced by Concevich, or also paper by Concevich Mani, around 94. And this is really the correct framework to study the compactification the modular space of holomorphic curves. So I just want to remind the definition, and then next I want to tell you a little bit about the topology on it, and then I want to discuss its compactness of the modular space. Okay, so let's start with the following things. Sorry, let's start the stable curves. Okay, so this is actually, so without maps, or maybe you consider targets just a point, then you have only domain, and then the notion is actually the so-called stable map. I don't know, stable curves. Maybe studied by, I don't know, people may attribute it during the month. Okay, so what it is. So let's see via a singular Riemann surface. So maybe it may contain several Riemann surfaces. So C1 to Ck are compact closed Riemann surfaces. Or maybe the algebraic curves with, at worst, the nodal singularities. Namely, locally, so singular points. So singular point is only the following type, like locally. So in C2, you have C2 here, and then you have two coordinate axes like this. So therefore, it was maybe Z1, Z2 is equal to 0. So this is the allowable singularity. So you have Z1 equal to 0, then you have this line, right? Z2 equals 0, give you this line. And so this is a singular point we allow. So this is a nodal point. So we consider, say, several closed Riemann surfaces, and then just allow that kind of intersection things. So here it may be vague, but this is for people may call it maybe pre-stable curve. And now I define this automorphism, right? So or maybe we may also have a mark point, right? So mark point on a curve, or on the Riemann surface, right? So this is just maybe say Z1, Zk are just a distinct point on this C. So C is just this union of closed Riemann surfaces, and then Z1, Zk are distinct points on C, so that Z1, Zk never coincide with singular point, never coincide with nodal point, away from nodal singularity. So if I write, so the picture is always, just a cartoon picture, because I cannot really write any real picture here. So mark points are just points somewhere like this. So Z1, Z2, Zk. Something like this. And okay, so sometimes you consider this C, maybe I know by Z vector. Z vector is this Z1 to Zk. Okay. So this thing we may call it K pointed pre-stable curve. And now we consider its automorphism. So now we consider automorphism of this thing. Maybe only C, or maybe with these things. So automorphism group. So what does it mean? So this one is mapping like a phi from C to C. And so for each component Ci, it is just a Riemann surface. So therefore, phi restricted to Ci is a bihomomorphic map to its image. And nodal point has to be mapped to the nodal point, and in a consistent way. So therefore, maybe I just assume phi is a homeomorphism. Of this C. And finally, for each marked point, I assume that Gi is mapped to Gi for any I, 1 to k. So this is automorphism. So C is a union of the Riemann surfaces. So each component has a holomorphic, it has a complex structure. And then we can talk about biholomorphic map. So this one says that Ci need not be mapped to Ci. Maybe some component may be exchanged. But anyway, this one is a bihomorphic image. And homeomorphism this phi should be homomorphism. So therefore, there is a kind of permutation of components and permutation of the nodal points, but marked points are just mapped to itself. And so this is automorphism. And then we say that the CZ, definition of this thing is CZ, this pair, is a stable curve if and only if this automorphism group is finite. So this is the definition. And if you just look at each component, we can also say the following. So let Ci be a irreducible component of this C. Okay? And then for any irreducible component, we just interpret this condition as follows. So then for C, actually either genus of the Ci is bigger than or equal to 2, or genus of Ci is equal to 1, then the number of marked points on this component Ci and number of marked points on Ci and nodal points on Ci. So this must be at least, they must be this one. Or maybe because genus Riemann surface is just a closed oriented surface, so therefore the remaining case is just a genus of Ci is equal to 0. And in this case, actually, the same thing is at least 3. So this is a condition for this, right? Certainly, we have only finite many components. So here I have only finite many components, and so finite many nodal points. So therefore, you can also say that if this is stable, if the automorphisms, so that phi is a bifurcation map of Ci, and nodal points are mapped to itself, and nodal points are mapped to itself, and mark points are mapped to itself. Such a thing is finite. So this is the same thing because anyway, finite permutation, finite object is just finite group. So therefore, this is you can just understand this. So this is just a definition of stable maps, stable curves, and then you can just consider the following. So then the moduli, so it has a certain moduli of stable curves. So in order to talk about this, I need to introduce two things. One is actually genus, and another is actually number of mark points. So the second one is just the number of mark points. So K is just the number of mark points. And for genus, actually this is the following. So say you have this say you have this. What is the genus of this? So genus of this is the following. So here, this is genus 2, right? Genus 2 component. And this is genus 1 component. And this is genus 0 component. Maybe genus 0 component, and genus 0 component, genus 1 component. Right? So for each component, you have a genus. But also we can talk about the dual graph. So namely, the vertex of its dual graph is a irreducible component. An edge corresponds to the node joining 2. So in this case, actually, I have 1, 2, 3, 4, 5 component. So therefore, I have 1, 2, 3, 4, 5 component. And then there is a node here. So therefore, I have parts like this, and I have this, and so I have this, so this, and this. So in this way, we can talk about the dual graph. And then here, you can talk about number of loops, right? So here, you can talk of number of loops. Maybe what does it mean? So number of loops is actually the 1 minus the Euler number of the graph. Okay. So in this case, after Euler number is 0, so therefore this is 1. I have only one thing, right? So because so it is nothing. It is nothing. But if your graph is like this, and then here I have a loop, and here I have a loop, and you may think that this one is also a loop, but we don't really count this and this and this to get 3. Look at the Euler number of this. The Euler number is, the 1, 2, 3, 4, and edge is 1, 2, 3, 4, 5. So Euler number is actually minus 1. So therefore, 1 minus minus 1 equals 2. So I just look at this, right? Like a first bit number of the graph. Anyway, so this is the loop number of the dual graph. So maybe better to write maybe B1 of the graph. Okay. This may be better. Okay. And then this genus of C is defined to be the sum of the genus of all components Ci. So I run from 1 to k there, and then add, maybe I just write a B1 of the dual graph. Okay. So this is a genus. And why do we call it the genus? So the reason is the following. So if you have this nodal singularity, originally you have Z1, Z2 is equal to 0, but you can smoothen it to maybe a Z1, Z2 is equal to epsilon, right? Then what you get is something like this. Something like this. And in this picture, so originally my domain is somehow has 2 parts, like this part and this part, right? So two disks are meeting. So because here this line is actually small two disks, right? 2 disks intersecting transversely in C2. So here I have 2 disks. Yeah, I can write them transverse, but anyway, I have this. And then what we do is somehow we just smoothen it like this, right? And then just continue to this, or continue. And then after smoothing, you get a genus 3 curve in this case. So in this case, if I smoothen this, then here I can smooth this here, and then I can smooth it here, and here. What we get is actually, so here 1, 2, 3, 4, but I have another genus here, so therefore this is genus 5 curve. So this 5 curve, actually this loop is actually coming from this. Right? You just consider this, and then so therefore it's quite natural to add this effect for this case. Okay. So now we just collect all of them, and then this one is written as M, G, K. Okay. So this is a stable curves of genus G, and number mark point is equal to K. And it is known that it is a compact Hausdorff space, and in fact it has a obifold structure, compact Hausdorff space, and also it is an obifold, complex obifold, or maybe B minus. So this one maybe people may just refer to during a manifold, and so they actually don't call it an obifold, but maybe it's a stack. But anyway, so it's a nice space. And how can we understand this? So this one is okay. So sorry. I have to assume something. Yes. So here, I have to assume this. If G is bigger than or equal to 2, then it's okay. And if G is equal to 1, then K must be at least 1. Or G equal to 0, and then K must be, not K. Sorry. Yes. Okay. K is equal to 1, and G equal to 0, then K must be at least 3. So we have to assume this. Otherwise, we may not have any object, so therefore it may not be the case. For instance, if G equal to 0 and K equal to 0, certainly we have CP1, only CP1. So it's just one object. So you may think that it's the one object, it's okay. But this one has automorphism. PSL to C. Right? And so it's infinite. So K equal to 1, K equal to 2. Still you have non-trivial automorphism. So this is 6 complex 3-dimensional things. And here we have a fine transformation group on the complex plane. So therefore here after dimension C is equal to 2. And here you have a north pole and south pole, and then the automorphism is just kind of multiplication by some complex non-zero complex number. So this is actually 1-dimensional. So anyway, so all has non-trivial automorphisms. And if G equal to 1 and K equal to 0, then in this case you have certainly elliptic curve like this. And so elliptic curve is actually, as well known, this can be written as a quotient of complex plane by certain lattice. So the tau is in this upper half plane. And so, but in this case, actually, if you consider automorphism of this, this one contains this one itself by translation. Yeah? It's a torus, and you pick one point somewhere, and then you can think of it as a river, and then this one translation. Sometimes you have finite extension of this, but anyway, you have this. So therefore, it is not stable. And if d equal to 1 and k equal to 1, then you have a 1 point on the elliptic curve, and then you can kill most of the automorphisms. And then you have a very famous picture. So this, I don't know, very famous picture, right? This picture like this. And these two are identified, and these are also identified. And so this one, actually, from here, actually you can get this complex plane. But in fact, here and here, you may think of it as a singular point. But anyway, so like this. And so this modular space of, so here actually I need to put 1 point somewhere to kill the automorphism. But then if you look at this space, so this one is non-compact. So to compactify, you need something you need to add something. And that is a nodal curve, right? So if you go to the infinity, and what you add is somehow this object. I don't know, this picture may not so appealing, but something like this. So I have a P1, and then I just take 2 points, say North Pole and South Pole, and then I just identify them to a point. And in some local model, I just put it in this way. Then make it a nodal point. And so here I may take 1 point somewhere. And then this has no automorphism, because you have 1 point here. You just separate these 2 points. You have two points. It's interpolation with that one. And then you have additional point somewhere here. And then you have 3 points on P1. So then the automorphism of this domain is trivial. So therefore, this one has no automorphism. Right? Okay. So this one is compactified by adding this sort of behavior. But maybe we can also interpret it in terms of two-dimensional hyperbolic geometry. So if you have this C and this Z, and then somehow you can remove C minus this Z1 to Zk, then you have this punctual Riemann surface, right? And this punctual Riemann surface, let's suppose that C is irreducible, okay? C is irreducible curve, and then remove those points. And then the Euler characteristic of this guy becomes negative. And so therefore, it carries a unique hyperbolic structure, hyperbolic metric, conformal to, compatible with the complex structure. So C is now I say C is a Riemann surface, so therefore complex structure already assigned there. So I have one complex structure there. In particular, it gives you, therefore you have a conformal structure there. And then it says that, so there is a hyperbolic metric on the surface. Underlying conformal structure is compatible with this complex structure. So this. So you can think of such a stable curves as a oriented surface with hyperbolic structure, and these are actually the cusp points. So therefore, it has a finite area. Yeah? So therefore, maybe we can also write it with finite area. So not arbitrary, not arbitrary hyperbolic metric. Hyperbolic metric may have hyperbolic structure on the surface. May have some infinite things, but here we only consider because these are punctures and so therefore correspond to cusps and so and so now I have a sequence of this Cn, maybe this Zn, right? So I have a sequence of stable curves, and then here I have a sequence of hyperbolic metrics corresponding to this. So Gn is a corresponding hyperbolic metric. With cusps, with finite area, and this is same as cusp. And so then what we can say is either it has a limit like C infinity and Z infinity. So this is actually certain hyperbolic structure with cusps, or maybe so C infinity is same as underlying one is same, or it has a thin tube, so or apart or decomposed this into some components joined by the thin cylinders. Something like this. So what does it mean? So you have some surface here, maybe some marked points, and then maybe hyperbolic structure changing. So therefore, it is not really constant, but the hyperbolic metric somehow converges on the same underlying surface. That is the first case. Otherwise, other case is that some part. I mean, here, say I have some closed geodesic here, and this closed geodesic is getting shorter and shorter, and then degenerate to a point. In such a case, because of this hyperbolic structure, actually it develops really thin necks. And so getting like this. And in the end, it decomposed into two. So here I have one thing here. And another one is also coming this. I cannot write because they are infinitely long, so therefore I can write this one on the same line. But anyway, so it actually decomposes into two things. So somehow the statement is more precisely, if none of closed geodesic shrink to a point, none of the geodesic, all closed geodesic don't really collapse. In other words, there is the lower bound for the length of closed geodesics, and then such a thing cannot happen. In such a case, actually the metric actually converges on the same surface. Otherwise, it must develop this sort of phenomena. Okay, so this is actually the statement found in two-dimensional hyperbolic geometry, and so that actually also explains you what the limit object here, right? Because you start from this, and then you have a complex structure and complex structure gives you this hyperbolic metric. And you have this hyperbolic metric, you have a metric, so that you have an underlying conformal structure, and then also you remember orientation, and then you can recover the complex structure on the Riemann surface. So therefore, this is somehow, just remember the orientation, then this hyperbolic structure and the Riemannian, the structure as a Riemann surface, actually there is one-to-one correspondence. And then this one, so how it behaves. So either the metric converges to another metric on the domain, on the same curve, and then this limit thing, you can also think of the stable curve. If it is not the case, then it must develop this sort of phenomena, and then it decomposes into several components. And then if we look at this, in this case it is just like this, but maybe it may happen that you may have this sort of, I don't know, maybe my picture is not so good, but it may have this sort of case, right? So locally it may develop such a thin neck several places, and then if you consider this component, then it has several ends, and so I have the corresponding vertex here, and then it has several edges emanating from here, and from here actually I also have an edge emanating here, and then here, and then this one also like this, right? So therefore, you can get this kind of dual graph. So genus actually is controlled by this genus of the genus of each component, and also the V1 of the dual graph, right? So therefore you can actually see that what kind of limit you can get. Yeah, they are actually these stable curves. So here you can only have these very simple things. But here actually it is not really like this, but somehow you can actually make it one-to-one correspondence. So one thing I want to say is the following. So, for instance, if you have this very nice picture like y squared is equal to x cubed plus lambda, right? In CP2, maybe I have to add, so here I have a homogeneous coordinate like x, y, z, right? And then I should make it a homogeneous cubic polynomial, so therefore maybe I put z here, and here maybe I put z cubed, okay? When lambda tends to 0, this one is converged to y squared z is equal to x cubed. And I think so. But if lambda is non-zero, they are all conformally, all bihomomorphic. They are all bihomomorphic. Just to change the coordinate by just multiplying some constant to coordinates. Actually, they transform each other, so therefore they are all bihomomorphic. And this one is different, right? So this one maybe this is they are all elliptic curves, but this one is different. So this one, if you write it, people often write it like this, right? it's a cuspidal cubic curve. And this one, I think this one in this case maybe just a usual elliptic curve. And so therefore, if you just look at this phenomena and then you look at this elliptic curve and this cusp curve, then you may think that this is actually doesn't really fit this. But in fact, we don't really think we don't really consider such a thing in this case. So certainly, yeah. So we have to really discuss this. But so please just yeah. Okay. So in the case of elliptic curve, and with map points, then there may, yeah. So you have a sequence of metrics, a sequence of Riemann surfaces, and then this kind of closed geodesic may shrink to a point, and then you may end up with these things, right? So this is not a picture in hyperbolic geometry. In hyperbolic geometry, maybe I cannot write it because this part is also going to infinity, and this part is also going to somewhere infinity, right? But anyway, so this is not a realistic picture, so because this one is not embedded anywhere. So in fact, this one is actually this limit, right? This limit. So therefore, you get this one. So this happens. We include such a thing in the moduli space, but this cuspidal one is not, right? Because it's a constant in the moduli space, and so it cannot really converge to something else. Okay, so this is one thing I wanted to say about stable curves. Is it? So now I come to the stable maps. So I think the idea by conservative is just the following. So you consider moduli space of holomorphic curves, and then you want to compactify it. Then somehow you have to take this sort of thing into account somehow. So therefore, in order to have a nice moduli space, like a Hausdorff moduli space, and then certainly you have to assume the finiteness of automorphisms. So in this case, just assume finite automorphisms, and then you get a nice moduli space. And so here, so first of all, it is a continuous map. So let's F, right? So F is a continuous map. And then if you restrict F to each component, this is actually holomorphic curve, so J holomorphic curve. And then finally consider the automorphism group of this thing. So this C, Z going to X, right? Is finite. So these two are just no condition. Just F is a map from C to X. So therefore it's just a continuous map, and each component you have their own map. And but this here assumes the automorphism finite. So what is the automorphism group? I erased it. So maybe I have to I should keep it somehow. So K Z equal to 0 and K equal to 0 here. So I come back to this. So what is automorphism of this thing? this is, yeah. If we are asked, then it is really natural concept. So this is actually a automorphism of the domain curve. So phi is the automorphism of domain curve. So that this one preserves the mapping F, namely F composed with phi is equal to F. So you have C here going to X, maybe Z here. Okay. So yeah. And then here you have CZ, you have biholomorphic map phi. And then just to consider this picture, right? So if this one commutes, and then we call this phi, biholomorphic phi, the automorphism of this map. So this is actually a subgroup of the automorphism on the domain curve. But this one is not stable, but just pre-stable. So therefore, as I wrote there, if we have a component of genus 0 k equal to 0, or k equal to 1, genus 0 k equal to 1, or genus 0 k equal to 2, or maybe genus 1 and k equal to 0, and then this group itself is infinite. But now we assume this condition. Okay? And then what does it mean? So these cases are somehow, this condition is something, right? So now I consider case of automorphism of stable or pre-stable map. Map from the stable map, pre-stable curve. And so in this case, actually, so if your curve Ci, your one component Ci is genus 0 and k equal to 0, and then this one is infinite. So therefore, domain itself is not stable. But now you assume that this restriction of F to Ci is non-constant. Then this one, the automorphism preserving non-constant holomorphic map. I assume only holomorphic maps here, holomorphic ones. Maybe it is not really necessary, but then actually this one is yes, this one is finite. Okay, so like if you only consider smooth maps, and then here you have a domain like P1, right? CP1, and then if your map just to collapse the horizontal circles the point, and then you have a map like this, right? And then this one certainly non-constant map, but certainly this rotational symmetry preserving map. So therefore, it is not finite. But in my case, actually, I only consider holomorphic maps. So therefore, the non-constant condition is enough to say that this is finite. So similarly, here and here, and here. Okay? So we have several cases. The domain component, irreducible component domain, unstable, and then we require that the mapping on such components are non-constant. So now I can say that yes. So here, the domain, irreducible component domain has either genus bigger than or equal to 2, or genus is 1 and k is bigger than or equal to 1, or genus 0 and k is bigger than 3, or the mapping is non-constant on that component. So in this case, actually, we don't have map, so therefore map is constant, so therefore, but if we have a map, then we just consider the moduli space, the stable map, not only this, but also non-constant on the component. So this is a definition. Okay. So now I gave this example. So this is actually a sequence of holomorphic maps from elliptic curve to CP2, and image is just like this. So you have a sequence of holomorphic maps from elliptic curve to CP2 with this image, and then you have a sequence of such maps, and then what is the limit of it? But geometrically you can only see this. So this is the picture like this. Or maybe I can also give you another thing. So you have a line here. Again, this is a CP2. You have a line here. So it's a line. And you have another one is conic. And line and conic certainly generically intersect 2 points. So you have 2 points like this. But line moves. So conic may be fixed. And line is actually moving. And eventually it's finally tangent to this. Okay? So conic is the rational curve, and line is the rational curve. So therefore, I may just write the following way. So I don't know, maybe using this. Sorry. Maybe using this. So I have two P1s, so both are P1s. And red one is mapped to, say, this red one, right? And the yellow one is mapped to this one. And so then they meet at 2 points, and so here I have 2 mark points. And here we can also have the same thing. Right. And in the end, I have here line here. So I have something like this. And then I have a conic here. So this may be like this, because meeting at 1 point, right? This. So is this converges to this? So if you just look at the limit and then the parameterization of the image, and then you have the sequence of maps, which is actually mapping from the 2 copies of P1 meeting at 2 points. And such a thing that these two are both unstable, because P1 with 2 map points is unstable. But anyway, mapping is non-constant. So these are stable maps. And so here we have such a parameterization here and parameterization there, and so. But in here, actually, in the limit, I can only see these 2 curves, and then is it a limit? So as here, actually, somehow we expect that modular space of stable maps has nice property, like a compact Hausdorff. Maybe in some good cases, a multiform structure, and just G and K. But here, if you look at it, this is genus 0 and genus 0, but here is one loop, right? This is actually the dual graph is just like this. So therefore genus 1. So genus 1 curve, and then finally this one is genus 0. So genus is lost if this thing is correct. And then certainly the moduli space of stable maps with fixed homology class and fixed genus and fixed number mark points and so on is not compact because it is not, right? So therefore, this is not really a right thing. In fact, this one is not the case. This one is not the case. So that's somehow I want to explain next. So what is the convergence of stable maps, right? So the topology on the moduli of stable maps. So for simplicity, I just talk about the limit of sequence. So let's suppose that I have a sequence of stable maps, sequence stable maps, and also I assume that this thing is some fixed. This one is fixed. So if we don't fix this, then certainly we don't have any energy bound. Yeah, if you have this and then you have energy bound, so if you have energy bound, you may expect the compactness, as I told you before, because at least away from finitely many points, it has a converging subsequence, and also around that point, if you rescale correctly, and then you make some other components. Maybe it's not enough, but maybe you can do this. So this is. And then ask whether, and also I have another one, like a C and Z to X, right? So I have these two things. So with the definition, right? Definition, this Fn converges to F if the following thing is true. This may be a little bit tricky. So I have to give the definition of this. So roughly the following thing. So there is a here the number of mark points are always k. Okay, number of mark points. And maybe Cn, genus of Cn is equal to G. So this is a genus of a stable curve. Yeah. But anyway, so then the following thing. So there is another one, like we may often write Z plus N and Z plus. They are the mark points on C and C. So they are additional mark points on Cn or C and away from Z N and Z, and possibly nodal points. Always we assume that mark points are away from nodal points. And here we also assume that these new mark points are away from the previous mark points. Okay? And then if you consider Cn, and then Z plus, sorry, Gn union G plus of n. So I add mark points. So originally I have k mark points, and then the domain may not be stable because the map may be non-constant there. So the domain may not be stable. But by adding certain number of mark points, certainly we can assume the domain is stable. But anyway, so this is the first one. And more than that, so this one actually converges to this. So this is the first condition. In the moduli space of the stable curves, genus G and K plus K plus or something. Okay? So I just assume the number K plus. So this is the first one. So this is in the Green-Mumford moduli space. And secondly, our map Fn converges to F away from nodes. Sorry. Maybe. Okay. Away from nodes. Yes. Sorry. Maybe I have to write it different one first. Maybe different one. Okay, so C prime. Okay. Yes. Yeah, maybe for simplicity, I just assume this. I will mention this a little bit later. So okay, so away from nodes. And near nodes, actually the diameter is very small. And near nodes of this C, so diameter of this Fn in a near nodes is very small. So this statement is not really rigorous statement, so I can tell you what does it mean. Okay. So originally, our domain curve is not stable, but first we add some mark points, and then so maybe I have some mark points here, and then maybe I have another one here, and then maybe for instance this is P1, and then maybe I need to put some mark points here, right? Like this. But this is not enough. This is not enough, but at least we have to put to make the domain stable so that we can talk about this convergence, because this one has to be an element of certain moduli stable curves. So therefore, I have to put some mark point like this. And then, then it may develop another kind of thing. So here I have this Fn to x, right? But then it may develop other ones like this. For instance, like this. I don't know, something like this. But not only this, we may have some other sphere component here, like if some derivative diverges somewhere, and then derivative diverges somewhere, then we may have another sphere component. So something like this. And then I need to add some mark point here. So therefore here, so in the limit somehow we have this picture. Then on the domain actually I have this red one, and here actually originally it is not stable, so therefore in order to consider element here, I put one mark point there. And then I need to add some mark points here, right? If you just smoothen this part, right? So if you smoothen this part, so here I have like this, but here it may develop this sort of stuff, right? And then this one is conformally equivalent to some Riemann surface like this, and then this point is corresponding to something there. So this is actually the definition. So therefore, what I'm saying is, so for this Cn, you take a certain number of mark points, and in the limit, I also take some mark points, and then this one, after taking this red new point, it converts to this in the moduli space of Riemann surface. And so now we have this map like F. So I assume that this one converts to F. What does it mean? So away from nodes means away from nodes here. So I have C. So away from nodes of C. So because they are so close, so away from nodes, we can add, somehow we have a diffeomorphism from this part and this part. Yeah? So if we just remove some part of this, and then this is this. And here, it's not so easy to see, but here I have something like this, right? Is it okay? So locally, I have this red point, right? And then I have something like this. And then surface is somewhere like this. Like this. And so if you look at this in a different picture, maybe it can be written as this. So here is this kind of bubble here, and then you have a kind of neighborhood in here. So near here, because this is very close to this one, so therefore here I have a long neck, as I mentioned with this hyperbolic geometric picture, and so we have some rather long neck. And so here, actually, even though I'm writing rather short neck, it's really long neck if it is very close to this. So anyway, so I have this, and maybe here I may also have this kind of stuff. Yeah. So away from this yellow one, then somehow we can identify the complement of yellow guy with the complement of yellow guy in C. And then I assume that on that complement of yellow guy, how Fn and F close. And somehow what I'm saying that this one converts to F away from the yellow ones. And another one is, in this yellow region, actually the diameter is so small. Because here, it is actually a node. So I have two components, two disks meeting there. So two disks are mapped to the manifold. But two disks are conformally equivalent to infinite cylinder, right? So if you take a puncture, then so you have a kind of exponential decay estimate. So therefore, here actually, if you take this neighborhood so sufficient small, and then actually image, right? And then here actually it is very conformally equivalent to a long neck, and then today I mentioned something like a behavior of holomorphic map from long neck, long cylinder to a small neighborhood of some point. then it's also kind of exponential decay. We also, yeah, all the derivatives. So therefore, in this neck, actually, we assume that the image is so small, and then somehow automatically imply that all the derivative also satisfies an exponential decay estimate. So this is a definition for this, roughly speaking. In fact, in this process, we may get more component, and then we have to throw away some of the component if it is if you forget this. So first I have this, but what we want to talk about the conversion from here to here. So therefore, somehow we want to forget this at the end. So there may be some component which is stable because you have this marked point. So if you forget this marked point, then it will not be stable anymore. So then we have to throw away. But anyway, this is a little bit tricky things. And then I can just come back to here, and then I just want to tell what is a way to understand the limit. And then I stop, right? So the idea is very simple, but yes, I don't know. So I have this red one and yellow one. And so in this case, I have these domains are unstable. So therefore, in order to talk about this, maybe we have to add 1 point on each domain component so that it becomes stable. But that is not enough. That is not enough. So therefore, here this is not just making the domain stable. So what we do is the following. For instance, for this red one, for this red one, I take maybe 2 points, like this and this, and so maybe it looks so strange, but maybe just let me write this picture. So I want to consider these 2 domains become stable. Not this one, but this one. Then here I have one special point, but I need to add at least 2 mark points on the domain. Right? So I just want to put mark point on the domain. So therefore, I need to put some mark point on the domain like this. Okay. Then I also want to put a mark point on the previous ones. So how to find such a point appropriately? So I just put this codimension to transversals. This one is a surface, so therefore it's a 2-dimension in the manifold. So I just take a small transversal of codimension 2 at this point, right? So I have this point, this point, this point, this point. So there I just put some transversals there. I put transversal here and here. And then here, this one stay here, maybe stay here, and this one may stay here and stay here and so on, right? Okay. Is it clear? So I have here CP2. Okay. I have here CP2. And then inside, I put 4. Codimension 2 surface, but just a piece of surfaces. And then consider the intersection of each component. So in this case, maybe in that case, so this one maybe intersect with this, like this. Then this intersection point gives you a mark point on the domain. So this one gives you a mark point on the domain, maybe here and here. Right? And the red one, maybe my red one is not so good, but my red one may be like this, and then the green one may be like this. And then we have these 2 intersection points, so therefore we can put these two mark points here and here. What happens for for these points, right? But we also have these two additional points correspond to the nodes. So we have to look at this configuration of 4 points, not only this and this. They are new mark points. And these are the points correspond to the nodes, right? So in the domain, yellow domain, I have just sphere here. Okay? And then just fix this parameter. I just look at this picture itself. And then I have point here and here, right? It is just this one is fixed. So therefore, I have fixed 2 points somewhere. Okay? But now I have 2 mark points. And now my 2 mark points actually, so this corresponds to these 2 points, Right? But as n tends to infinity, this line is getting close to the tangent line. That means these 2 points are getting closer and closer. So therefore, you have a moduli space. Here you have a moduli space of genus 0 and 4 mark points. Right? And then if you just consider the limit of this, the limit of that is nothing but this thing. So this is the Riemann manifold compactification, right? Maybe in the case of rational curve, certainly you can also use you can explicitly discuss with I forgot cross ratio to parameterize the object in the modular space of genus 0 curves. But anyway, so this is a limit curve. Is it clear? So here actually I have 4 points, and then as n tends to infinity, this yellow one is fixed. So therefore, these 2 points maybe I just fixed here. But if this red one is getting close to the tangent line, and then these 2 points are getting closer and closer, and then they coincide. But for stable curves, the mark point should be distinct. So that I mentioned at the beginning, right? I already raised. So at the beginning, I said that mark points should be distinct. So to be distinct, you have to make this domain. You get some this domain. So therefore, this is the domain of the curve. And same thing happened here. So in the end, what you get is this. So I have this red one. So red one, but red one is here, right? And then this red one maybe just coming to this red one. And the yellow one is this yellow one, and this one. And then I have these green points. So green points are here. So in fact, I said that this limit, asked whether this limit is this one. But what I'm saying is these two appears here and here, and there are additional components joining them. And so you have a map. So in fact, from here to here, so from here, from this component, it is actually mapped to this, right? And from this component, it is mapped to this tangent, conic. But this one, the whole of this, is mapped to this point. And this one is also mapped to this point. So I have 4 components, 2 components actually as they are, and we have additional 2 components. It just contracts a point. And these 2 are stable because I have 3 special points. Like I have 3 nodal points. So therefore, these 2 have trivial automorphisms, right? although the domains, the image is constant. So therefore, this is a way to get the limit. So I didn't really give you the precise definition of the convergence of this mapping, but I need these three things. So I need to add more map points. This is not just making the domain stable, domain of the sequence stable, but also the domain of the target stable. And possibly more points are necessary, because when we have this bubbling phenomena, somehow we also handle this kind of component by adding map points. So maybe I have no time to tell this, but the idea is somehow you consider the point, if some derivative diverges somewhere, then you just put 2 points near such points. And then keep them away for some time, because they cannot collapse in the moduli space of stable curves. So therefore, you put 2 mark points. That means somehow they are kept away. So if you consider the family of stable curves, and then we can put certain family of metrics on such a stable curves, and with respect to this metric, actually 2 points, the distinct points are somehow kept away. And so therefore, if the derivative tries to diverge, and then we just to put two mark points there, then they cannot come close cannot come closer. They have to put away. So therefore, yeah, we can put such a. So therefore, after taking such a additional mark points, and then we can also handle the bubbling phenomenon. And such a thing only happens finally many times, because each sphere component, the non-trivial component, has certain energy, but total energy is bounded. So therefore, you have only finally many such possibilities. So the compactness of the moduli space stable map is somehow, yeah, similar to basically the argument for this bubbling argument and so on. But yeah, in our case, actually, the domain the complex structure of the domain may degenerate, and also maybe you have a lot of bubble sequence. But anyway, so this way somehow you can also handle all this. So that's all today. Is it okay? Actually, at the beginning, I also planned to speak a little bit about Lagrangian structure, but probably no time, so therefore. So I don't know, this time probably I have no time, but maybe if it's necessary, maybe I can give some time later. Not this time, maybe next time. Next time means next year. Yeah, no, because the next month, actually, I will speak about toric case, right? So therefore, I have no time for explaining the virtual technique. But if somebody is interested in virtual technique, and also I also plan to tell why do we need such technique. So monotone case or so-called semi-positive case, for some purpose, we don't need to really use such a technology. But in general, we really need it. And so probably it's already over, but maybe I just mentioned this. So so the idea is the following. So actually, this is maybe originally, maybe due to Gromov, and then maybe presented by McDuff several times. And so actually, he actually used the so-called inhomogeneous perturbations, and she also discussed some Floer injectivity stuff, and those actually gives you the transversality issues. No? Maybe this is just this. So so you have this d bar equation maybe from sigma to x, and so either you may consider this d bar of f is equal to mu by adding certain term, certain perturbation term on the left, and then sometimes you can achieve the transversality. Yeah, because what we consider is somehow basically you have something like a W1P maps, and then over here you have certain Banach bundle here. But maybe you can just consider local picture. So locally you have W1P space, and then over there you have just a trivial Banach bundle over there. And then this d bar equation is just a section like this, and this is so-called Fredholm section. That means its linearization operator is actually Fredholm. So it is non-linear, but somehow linearization is Fredholm. And so if I consider if I make this section transversal to the zero section, and then the zero set is certainly a manifold by implicit function theorem and so on. So if I consider zero section here, and then if d bar is a section like this, if they are transversal, and then certainly the zero set is certainly a submanifold of expected dimension. And this one is somehow you just perturb this zero section by other sections, right? By using this perturbation term, and then try to make transversal. And another thing is, so now I have a manifold xj. So for this, actually, we have a W1P map. And then here I have E here. But for this one, maybe d bar may not be transversal. If you consider the case like a -2 curve or -3 curve in algebraic surfaces, and certainly they don't satisfy this transversality. So now you consider somehow product with this space, and then consider parameterized problem. So here you take a map F and J, and then consider the section like d bar of J of F or something. So now we may vary J. So just vary J, right? And then somehow, more chance to make it transversal. So maybe I may just make it like this. There is one issue, because this one is a Banach space. And if I just stick to use C infinity almost complex structures, because C infinity one is good to get regularity and so on. So then C infinity, space of C infinity and the morphism are not really a Banach manifold, right? Banach space. But anyway, so there is a way to take certain subspace or certain subset of C infinity almost complex structures, which makes so that this one is a Banach manifold. So that is so-called Floer's C infinity epsilon. So there is some Floer's idea how to really consider this space as a Banach manifold. Or maybe you can also consider CK almost complex and so on. But anyways, you have this, right? So now, in this case, it may be possible that making this one transversal to the zero section. So maybe better to say the following. So maybe I just write it more precisely. So this DD bar thing is from this W1P map of this sigma and F star of Tx going to LP of sigma and 0,1 of T sigma tensor Tx or something. So linearization operator is something like this, and basically this one is as I wrote before this dd bar of j of psi is equal to just something like a nabla of sorry. It's something like a Cauchy-Riemann operator, like a, okay, so this is just a d bar operator with boundary on this, is twisted by this of psi plus something. And yeah, plus something. But this is maybe just a zeroth order term or something. So this is not so important. But if you consider this term, this is something like this, right? So locally, this is ddx of psi plus j of u of ddy of psi plus something like this. So now you fix j, then it may not be surjective. But now we consider W1P and j omega, right, to this LP. So this is somehow we now consider. So just add this part, right? So more variation. So therefore, we can actually change this. And then if you differentiate in this direction, what happens? So if you just take a tangent vector from here, like, I don't know, what is good? Maybe I or something, and then what happens? And so if you just vary this, and then j is actually changed to something like epsilon I of u, and so on, right? Sorry. Maybe better to write more precisely. Okay. So the Cauchy-Riemann operator of this u plus epsilon psi is equal to the ddx of u plus epsilon ddx of psi plus j of u of ddx ddy of u plus j of u and epsilon here of dy psi and so on, right? Something like this. So now I also vary j by I. Right? So now I want to consider the variation of this d bar and j plus maybe delta I of u or something. So not only differentiating this direction, but also this direction. And then this one is somehow the following. So here I have no I, but here I have something like dd delta of j plus delta I of du dy, and so on, right? So therefore here actually there is some effect. So from here we get something like I and du dy. So this thing is a kind of new contribution from here, right? So not only this part but also this part. So therefore then actually if you consider the image of this, so it may not be surjective. But after adding this, we have a new kind of contribution. So therefore, this new contribution may make the image larger, eventually the whole space. And it is true if the mapping is so-called somewhere injective. It is not so hard to see because, but maybe I have to write something else. So this is the way. So what is somewhere injectivity? So somewhere injective comes some inductivity is something like this. So you have F and sigma to X. We call such a thing somewhere inductive if there is a point P in sigma, so that the df at P is non-zero, and if you consider F inverse of Fp, this is just one point P. And this condition is equivalent to say that there is a neighborhood U of P, so that df listed to U is a immerse, maybe embedding, and F inverse of U is just U. So F of F inverse is just F inverse of F of U is just U. So you have a surface here, and then you have certain open subset, and then it is mapped to somewhere. And this yellow one is actually nice embedded piece of surface, and nothing else is actually mapped to here. Why such a thing is good? Somehow the point is we can so this is actually deformation of J, so deformation of something on the target. So we can deform almost compactly in the target. We just want to see the effect of the deformation this part, and then this only effect here. So therefore somehow, yeah, if we look at from this side, and then if we want to control something, then if we get something we want, and then we can do this. So, but the worst case is that if it is not such a map, say the multiply curve map, and then for any such a piece of surface, you have another effect here, and then these two contributions may cancel out, and eventually you can achieve transversality. So somewhere injective, then you can do this. So now I tell you what kind of thing is the problem. And if you know this, and then this is quite easy. So let's assume F is a map from here to here, and then you consider maybe sequence like Fn here, and then this Fn may converge to something. So, but this one may not be the same domain, but may have maybe with bubble, right? Maybe this one, maybe sigma with bunch of CP1 2x. Okay. So at the beginning, I have only have a map from certain things to here, but in the end, I may have a map from here to here. You may have such a thing. And then now compute the dimension of the modular space. So here, the homology class is A here, and then maybe homology class of this B here, then this is A minus B here. Okay. So the moduli of holomorphic curve in class A, and say genus G, what is the dimension? The dimension 2n plus 2 times C1 of Tx of A. Sorry. Maybe just consider the case of P1. Maybe that's easier. So now I just consider sphere. Maybe that is much easier for computation. So, okay. Sorry. Maybe that's much easier. So any domain is okay, but just consider this. So genus 0. Then this is actually this minus 6, right? And for this one, so moduli of holomorphic curves in class A minus B and B pairs of holomorphic curves are intersecting each other. And then this one is actually 2n plus 2c1b, c1txb, and then plus 2, so minus 4. So this one is mark point. And then another one is 2n plus 2c1 of tx a minus b, and minus 4. And I have to add them up, and then minus 2n. So therefore, this one is 2n minus, 2. This is actually 2n minus. It's really? Okay. So this is actually 2n plus 2 c1tx of a minus a, right? So therefore, if you just have an expected dimension, this dimension decreases. So therefore, yeah, in some cases, if this is 0-dimensional, and then this is negative dimension, so if you have a transversality, and then you can just get rid of it. Right? Like last time I talked about the bubbling of a holomorphic sphere or holomorphic disks, and then did some similar computation, and then actually, if this is dimension, the moduli is dimension at most 1, and then no such thing happens under monotonic condition. But in this situation, it is okay if all the transversals are satisfied. So this is just a computation, but so-called expected dimension computation. So both are not real dimension, but expected dimension. So, but if you have this sort of transversality, and then expect dimension is actually the real dimension. So, under some Fourier injectivity assumption, if this one, all of them are somewhere injective, then we can achieve this computation as a computation of the real dimension, the dimension in reality. But it may happen the following. So, but for instance, if so, I have this component like a fn, and then this one f, right? So let's suppose that if f restricted to b, I have two component, right? So here is a c1, c2, and say let's use this one is not somewhere injective. In particular, multiply covered, and then the dimension in reality may not coincide. Coincide with the expected dimension computation. So if you have this, and then certainly you can compute the dimension, but otherwise, in general, it is not. So let's suppose the following case. Let's suppose the case that C1 is actually, unfortunately, negative. If C1 of Tx is actually negative, and moreover, B is a multiple of some other class. So I have another map H from CP1 to X, so that F on the second component is actually a mapping like this. So if it factors through this M4 branch cover and map to X, then what happens? So I just want to tell you the dimension of this B part. There I wrote a 2n plus 2c1 tx of B minus 4 here. And this one, because of this one is equal to 2n plus 2m c1 tx and B prime minus 4. And then I compare it with 2n plus 2 c1 tx B prime minus 4. And when this one is positive, when this one is positive or 0, and then certainly this one is smaller than this. But so m is bigger than 2, bigger than equal to 2. But because of that, actually this one is actually bigger than this, right? Because C1 tx B prime is actually negative. So therefore, this one is bigger than this. Why this is a problem? Because what we want to have is the following, right? So here I have two P1s map to X, right? But let's suppose that you have a map like from here to here, maybe this F composed F over C1, right? And let's suppose that here you have a map like H. H is here, right? Then the dimension, expect dimension is somehow not this one, but this one should be replaced by this one. So therefore, the expect dimension of this one may not be larger, may not be smaller than this, because this one is differ by 2, but because this is bigger than this, so therefore it may be, yeah. And once you have such a thing, then we have certainly map like this, right? So then if you compose this, then you have this one, like F, right? So here, if you have such a thing, then this is just simply a geometric construction that taking M4 cover of this. So therefore, if such a thing exists, then you cannot really avoid it. Right? So if you want to avoid such a thing, then certainly you also have to avoid this. But because the dimension is not behaving so nicely, so therefore it is not the case. So this is the reason why, yeah, the transversality is in fact a problem in general. And so this is what we first called the negatively multiple problems, but still we can deal with it in an abstract way. So this is just one thing. So yes. Is it? Okay. Okay. Then that's all. Yeah. So okay. So this. Okay. So this one. I think this one okay. This one okay. This one okay. All right. maybe not so. Is it okay? Right. Yeah, maybe I just will give you something, and then maybe if you like to understand, then maybe you can look at some literature, and then you can look at some literature. And sometimes it's not so. Oh, sorry.